Okay, in the Sofia radiation experiment, we brought a Geiger counter on board and we measured the radiation on the tarmac before we took off. This is my AAA cohort, Kevin and David. That's me in the middle. And then we also measured it on the way up to the stratosphere. So it's a picture taken in the stratosphere of Mount Rainier, looking west. And so my question for you is, flying in the stratosphere, how is that going to affect the background radiation level? Is it going to be the same as on the ground, more or less? And what do you think? And it will be more. And it turned out that surprised the first people to bring radiation detectors up in balloon experiments over 100 years ago. They thought getting away from the ground, which was a source of background radiation, would make it go down, and it actually went up. And so that was a discovery. And so why is it more? And so is it the air in the stratosphere is radioactive? There's less atmosphere to block radiation, or Sophia's now flying closer to the radioactive stars. And the reason is, it is B. The Earth's atmosphere acts as a shield from the radiation coming from space that we call cosmic rays. And so another answer would be that there's more radiation from cosmic rays in the stratosphere than down on the ground. Here's our setup. I had a Geiger counter connected to a laptop. We also monitored our elevation, but that changed so much and the data was kind of noisy. We didn't really do a graph of the radiation versus elevation. We just have it versus time and just looked at what it was on the ground and then at its maximum. And so there's a close-up of the graph you just saw. And this is almost the first 2 hours. We weren't quite up in the stratosphere. Well, we weren't at our maximum altitude, let's say that, at this point. So the background did go up some. Also notice there's a lot of variability in the data. So it's kind of hard to say exactly what the background count is and also what that means. We did not calibrate the Geiger counter, so we can just talk about the relative background radiation in the plane at different times. And the Geiger counter is set to count how many radioactive particles entered it every 10 seconds. And so the pulse count here is how many particles came in each 10-second interval, and then we would put a little dot up there. So notice it does go quite a bit up from really close to zero on up to around 60 at this point. So why is this happening? Cosmic rays, mainly protons, coming from all kinds of sources, exploding stars and other interesting things. I recommend, if you're interested, just do a little bit of online research about cosmic rays and you'll find it's a very fascinating subject with lots of history and other related aspects, and you can even make your own cosmic ray detector. And so they're the main source of the background radiation that we're measuring. And this graph here shows what's known as secondary particles. So the cosmic ray, if we didn't have an atmosphere, would just zoom to the ground, and that would be bad because they are very high energy and it could cause problems for people. But instead they hit the air molecules and produce secondary particles. And so these are muons and pions and neutrinos, electrons, gamma rays, all kinds of things, and that's shown by this cartoon. And so the number of particles, not necessarily equating that with the radiation count or how dangerous they are, does peak somewhere up here well above the ground. This shows the elevation of a normal passenger jet, and Sofia is just a little bit higher than that. And so it's these secondary particles that we expose ourselves to, and there's more of them at higher energy up here. This cartoon sort of makes it look like there's way more on the ground. There's definitely a lot hitting the ground, and if you make a cosmic ray detector, you'll notice that, but there are way more up here. And this gives you an idea of what these particles are. All these could be produced by a few cosmic rays. And so the primary cosmic ray, again, the most common one would be a proton. Also some alpha particles, which are helium nuclei, but protons the most common, and they're coming really fast, a lot of energy. I think the most energetic one had the same amount of kinetic energy, same amount of energy as the kinetic energy of a fastball thrown by a major league pitcher. And that's a rare example, though. So it comes and it hits an air molecule and produces all kinds of stuff, muons and their associated neutrinos, as far as what makes it to the ground, and then also secondary protons, neutrons, pions, kaons, and then also the normal ionizing radiation, electrons, positrons, gamma rays, and then also you get some Cherenkov radiation, which is light produced when particles go faster than the speed of light through a material. And so just looking up that would be another fascinating research topic for you. And this was the count we took when we were at our highest elevation. And so we did it for about 10 minutes. And again, you can see there's a lot of variability, but the average is about 72 counts for every 10 seconds at this elevation, 43,000 feet, 13,112 meters, compared to the 2.2 average that we had on the ground. And so it does go up a lot. And so should we be concerned? And so this shows the average radiation exposure depending on your job for different jobs. And you can see aviation is the highest one on this list anyway. It is one of the highest ones, even above somebody working in a nuclear power plant. And that's because of this spending a lot of time. People that work on planes spend a lot more time in this radiation environment. But 3.07, that's again just from the flying, is similar to the typical background radiation every American is exposed to. 3.11, the units are millisieverts. Sievert is the metric unit for radiation. And here's some recommendations here to give you an idea of what 3.11 a year. The average 5-year recommendation to not exceed is 20. And so if do a little math, 3.11 times 5 is less than 20. So our normal exposure is not a problem. As far as how much you would get in a particular year, and this would be for maybe astronauts or somebody working with radioactivity in an extreme situation, if they're advised to keep it under 50 millisieverts in a given year. Fetuses are more susceptible to radiation. They don't have as much of the protective measures that an adult or somebody who's grown has. And so this is a recommendation for a pregnant crew member on a plane to not exceed 0.5 millisieverts per month. And so you can see if you multiply 0.5 times 12, that's 6 in a year. And if you add the background to this, that's sort of normal. But if they were a crew flying over the pole, they get more radiation there. That's because the Earth's magnetic field isn't as protective of cosmic ray particles there. And so somebody who's pregnant might keep track. You can find these online calculators that will calculate your dose depending on the flight you took. And they might even cut back their flying or ask for a different assignment just to be cautious. It's not, again, a huge health issue. And just also to give you an idea what a millisievert is, if you were to receive a dose all at once of 8,000 millisieverts or 8 sieverts, that would cause certain death. And so we're well below that. And this is a document where I found some of this information. If you're interested, you can look that up.